Can I get 3 small booms for the start of class?
Boom, boom, boom.
Looking at stuff. Today we have a small class, but like I said, I imagine people keep kind of trickling in here due to the weather. In this, we are going to start looking at stuff that historically, when I've taught this, has kind of thrown people for a little bit of a loop. We're going to avoid it because all the mistakes or issues I've had before, I'm aware of at this point in time. Really important, as always, if there's a part that we're talking about and you just don't get what's happening or why it's happening, what do? Indeed. Okay, so looking at this, I'm going to change the name of the section just a skosh from what it would be in your textbook. Today in 6.3, so it's the last section of chapter 6, but I realized that there was a winter break in between it, so before we test, we'll do review stuff. I'm going to give this a cooler name. We're going to be looking at relativistic velocities. Now, this sounds fancy. You could just use the word relative and it wouldn't change anything, but even that might be kind of, I don't know, unclear for you guys. Have you ever seen the word relative or relativistic with regards to physics stuff? You have. Do you know where? Okay, so there's some really cool ideas, and we deal with, obviously, we're at the beginning level of starting to talk about these things. Most famous physicist of the 20th century, who's in your mind? Einstein. Like, 100% it's Einstein. You guys know at least that Einstein was a big deal. Like, real big deal. Do you know why? So the theory of relativity is one of them. That's a big one, right? And then his special theory of relativity and general relativity, which you see that word showing up all the time. What does relativity mean? Or relative? If I talk about velocity relative to something. Was it the windows were icy?
And I had to take my little brother to school.
Okay, 50% will give it. Relative, what's it mean? Relative to something else.
Close.
So related or close, in my mind, I think with regards to, which is kind of it's just a salutation or the ending. What's the salutation starts or ends the letter?
That's the start.
Gosh, you are just wreaking havoc on my type 2 diabetes. I'm not. Yes, I'm not really diabetic. Thank you so much. I owe you one. Cool. That derailed me. Now, do you want to see what Einstein's big ideas were? Okay, how fast are we going right now? If I say 0, would you agree? Like right now, I am moving at 0. I'm not lying, that's true, but I'm also moving at like 800 miles an hour. Also true. Also moving at like 100,000 miles per hour. Also true. Why? How am I moving at 0? I am fast. What? But I am. Like, we're all moving. Why don't we feel like we're moving at all?
Because of gravity?
Maybe, depending on how you mean by that. When I ask you right now, if you look at me and I say, what's my speed? You're judging my speed based on what? On your speed? Kind of. Like, right now, if I make the claim I'm not moving, which I think is a true statement, can you give me evidence that I'm not moving? Oh my gosh, everything around me is in the same location, and I'm in the same location, therefore there's no change in position, right? Because when you see me not moving up here, you're looking relative to everything else around me, right? So, as we think about that, that's my 0, right? I claimed like 6 to 800, I just made up a number that was probably pretty close. How am I moving at 800 miles per hour? The Earth. And I'm moving at 800 miles per hour relative to the center of the Earth, right? Because I'm going in a circle around it, and we happen to be up nearer the top of the planet, so we move slower. Somebody at the equator moves faster because they have to go a bigger circle. Okay, nothing crazy there. What about the larger number, the 100,000? The solar system. Now, you've gone big, and there's probably middle ground in there. I know the Earth is spinning, so I could look at that speed relative to the center of the Earth. The Earth is also revolving around the sun pretty quickly, right? Like, that's happening. I could check that speed relative to the sun, or I could check our speed in the entire solar system relative to the center of our galaxy, which gets even bigger. And then we could start looking at, well, our galaxy relative to other galaxies. And there's just nowhere in the universe that we can say this is the point. And it's a weird idea. This is Einstein's kind of jumping in point and where his big ideas took place. Einstein is probably most famous for the equation E equals something. Do you know what it means? Good, and you started saying speed, so you were there too. Looking at it, Einstein's idea, that's his most famous one, is that energy can be converted to mass and back and forth between this constant, that's the square of the speed of light, which is pretty fancy stuff. The immediate implication of that is, well, we have nuclear energy, right? We can literally convert this mass of super radioactive stuff into this energy, and that's happening through a fancy process, but that's fine and dandy. Now, his other big idea, and this is a strange one, relates to time travel. A little bit. Okay. You guys ever seen the movie Interstellar?
Yes.
Okay, super awesome movie. If you've not seen it, they visit a planet that's near a black hole, right? Now, black holes, nobody knew they existed for real until like fairly recently, within the last 40 or so years. Einstein predicted black holes existed, and he was confident of it because his mathematics checked out, and some wonky things happens. On the planet, in Interstellar, when they're there, it's that big ocean planet, right? What happens? What's weird about the planet they visit? The time dilates. Okay, that truly happens. That is spot on. That really and actually happens all the time, and it happens even on small scales. Pilots fly a lot of time further away from the center of the Earth than us, right? Even if you're on a plane a lot, nowhere near as much as a pilot. Okay. Do we feel more gravity here or, I don't know, 30,000 feet above us? Where do you think we get pulled on stronger? Here, right? So what winds up happening is time moves slower for us. Now, it's not much. Astronauts experience the same thing to a greater degree. It's on the scale of like milliseconds for pilots and astronauts. But if you get far enough away or close enough to something really, really massive, like not just size-wise, but the actual mass of it, time starts to slow down. That's Einstein's big idea. You can time travel pretty easily. It's just getting to a black hole or something with enough mass to change the speed of time, which is a weird idea, is the issue. Okay, that is Einstein's big idea, and there's some even weirder things that pop out of this. If I'm walking right now at 2 meters, 1 meter per second, that's about this. Okay, I'm going at 1 meter per second, right? If I throw, something, right now I'm standing still. If I throw that at 2 meters per second, do you agree that I threw it at 2 meters per second? Sure. Okay, nothing crazy, right? Check it out. I'm now going to start walking at 1 meter per second. I'm going to throw it at 2 meters per second. How fast did I throw this? 3, but I saw it and I measured it and it was only 2. Why is it different? From where we're viewing it, right? It's that relative to what idea. This works with everything. If I'm flying at 1,000 miles per hour and I shoot something at 5 miles per hour, which is a super slow speed, it's now traveling from a still person's perspective 1,005 miles per hour. They just add up. Should that work with everything? Probably, right? There's one thing that's weird that it doesn't work with, and this isn't our focus, but I think it's interesting. If I'm traveling at the speed of light, let's go real fast, and I turn on a flashlight, what happens?
You don't see it.
Would the speed of light now be going twice the speed of light? Like, would it shoot out in front of me still? Or would I just never see the light spit out? And there's an issue, right? Now, the speed of light is constant. That is known to physics. It does not change. It's constant in a vacuum, which there's some more specifics. But it turns out I would still see the beam of light. Even if Abigail was going to turn on a flashlight the second I passed at the speed of light, and I turn on my flashlight right here, both beams of light travel at the speed of light. And it's a weird idea to think about. But what changes, and this is all Einstein's big ideas, and this is the very, very beginning of it, time changes. For me, time slows down so that I can still have that happen, and I don't break the rules. It's weird. Our universe is crazy. The code is broken. Not really. I don't think we're in a simulation. Or maybe I was programmed to say that. Anyway, this idea leads to really awesome stuff, but we don't get to jump in there. So, welcome to the beginning. We are going to look first and try to go kind of fast with the understanding that questions are super important. We're going to look at relative velocity in one dimension. So I'm just going to write 1D for one dimension. Okay, this is the natural situation where it's easy enough to think about. And our first idea, and it's going to be a vocab, is we're going to sneak in this idea or this word reference frame. A reference frame. Now, you'll see it presented like this. It feels much more natural for me to refer to it as a frame of reference, but they're the same meaning. All that this is, a reference frame, is a system or a coordinate system, which we can set up. A coordinate system. A coordinate system from which motion is viewed. Okay, that's it. We're just saying, where is the observer watching this happen? Now, there's easy places where we can distinguish between these. Do you want me to write the example from before that we just, the me walking example, or just want a quick picture? We should probably get at least a quick picture. Check it out. We have a person standing here, and they're watching. So I'm going to say, check it out, they're watching. And they are watching somebody roll by on a skateboard. And I need to make my skateboard better because that's going to bug me. Okay, so they're on a skateboard, and there's a person on the skateboard. That's not how a person's body looks. There we go. Okay, so there's a person on the skateboard. Now, hypothetically, and I'm going to use that they have a ball that they throw. If this skateboard is going, let's say, to the right from this observer, who is standing still. So we'll go ahead and say, check it out. The velocity of this person is 0 meters per second. And we're going to have to clean this up, but we'll get there. And how fast is the skateboard going? 10 meters per second. Okay, I'm good with that. Velocity equals 10 meters per second. And hypothetically, and this is hopefully going to be clear if you're listening and stuff, it'll make sense, but if you just look at the picture, it's going to be nonsense. They throw the ball at 30 meters per second. Okay. Now, if we said, how fast is the ball moving? This is that same situation that we just looked at. I just want to make sure we have it really down and we can see what's going on. As we look at this, from the person out here, they're looking, and the surroundings probably aren't moving, because it'd be weird if everything moved when somebody rolled a skateboard. Relative to the person, and I'm going to say observer. And this isn't a vocab, but it's a nice way to just kind of sneak it down. Relative to that observer, how fast does that ball move? 40, right? Because it's just a 30 plus the 10. And they would watch it. They'd see them add up. I'm good with that. V of the ball equals 40 meters per second. Okay, they could make that statement and they're correct. What about relative to the skateboarder? Or I'm just going to say skater. Relative to skater. What's the velocity of the ball? 30. Now, they're both correct, but all that's happening is they are viewing things from a different reference frame. One person's is moving, one person's isn't. That's it. Same idea. It works with every single thing that you'll ever encounter, even light, but time gets weird. Okay. Anything weird happening here? Okay, just to throw, don't change yours. And I'm leaning on this, and it's never, I do this occasionally. It's never dawned on me that this seems like something I'm going to knock down. Do any of your teachers use these as smartboards?
To like write.
Yeah, to write on it. Miss V does. Drives me crazy. All right, random thing. Okay, without adding it to your notes, what if this person threw this back, the ball back instead at 10 meters per second? To the person on the skateboard, it looked like they threw it backward at 10 meters per second. That's what they would see, and that's from their perspective. What about from the person on the ground?
They just threw it straight up. Or did they just left it?
So it's literally like you just see the ball stop, and it falls straight down. You guys old enough, was Mythbusters still a thing when you guys were younger? Some of you are looking at me like you've never heard of it. We're going to take a quick trip to the interwebs. As we look at this, we're going to be really specific with the way that we write stuff down. And oftentimes in this class, and pretty much all math and science classes, the way that you denote stuff and the clarity of your work plays a huge role in how well you're able to work through a problem. As we look at these, we're going to get our notation locked in, and then we will start looking at problems here shortly. When we look at something, this motion of an object relative to another, let's say we have an object A, and we're looking at its motion relative to an object C, or B. Let's look at it. Okay, I'm just going to write this down. The velocity, or the relative velocity anyway, the relative velocity from an object A this feels weird as I'm writing it, to object B, we can do it that way, to object B is written, and this is going to get more and more important as we get into some of these problems, but I'm going to let everybody catch up. So the velocity of A relative to B is how I would say that. The velocity of the ball relative to the observer. That's an example that we looked at. So as we look at this, the notation that we're going to use is the velocity of object A, and it's relative to what? B. Now, it's not a fraction. You can use a comma if you'd rather, but in your book, if you're going to look online, this is more likely what you're going to see. This is the velocity of A relative to B. This is how we write it down. Okay, now, when we start looking at this, we could use this at the example. I just used V here, but the velocity of the ball relative to what was 40 meters per second? And you don't have to add this in yours, but just so we can clear it up, the velocity of the ball relative to, who was viewing it at 40? The observer. Now, we commonly don't just use the observer, but if the observer is standing still, pretty safe to assume they're on the ground. So we typically use the ground. The velocity of the ball relative to the ground is how we would write that out. Now, this person's velocity of the ball relative to what? Where did we view it as 30? The skater, right? Or the skateboard. Either way, I would say, hey, this is the velocity of the ball relative to the skater. Now, there's one more in here that we haven't talked about yet, and I'm just going to address it here. This velocity of 10 was the velocity of the skater relative to what? The ground. Now, we're going to dig in 2 dimensions because the problems don't get necessarily any harder with it. There's a way to combine these, right? The velocity of the ball to the ground, the skater to the ground, and the ball to the skater. These all link together. And just like we see in pre-calc with matrices, when you look at the dimensions matching on the inside, notice that these match on the inside, and then these match on the outside. They're going to have a connection that we're going to be able to combine and make sense of the whole problem. Cool.
What is the SUG?
So this is the velocity of the skater relative to the ground. Ball relative to the ground and ball relative to the skater, because we're viewing it from all these different references to try to make sense of what's actually going on. Okay, so right up with this notation is what I want you to use. And it gets tiresome, totally get it. I'll show you where I cheat to try to make it a little bit less, but we're going to use this. Cool. All right. The relative velocity from an object A to object B. Or is this clunky to you? Okay, if it's clunky to somebody and you're worried about it, this is the velocity of A relative to B. A relative to B. Okay. As we look at these, what's going to get more and more important is our work with vectors and making sense of these in our motion diagrams, or specifically our free body diagrams. So when we go through them, it takes practice. You're going to be including pictures and free body diagrams on pretty much everything you do. And we'll recover the vector stuff because I think we did all that before Christmas, and you're probably rusty with it. So let's jump out of one dimension and let's start looking at 2D. So relativity in 2 dimensions. Okay. Now, obviously, we don't live in a 2-dimensional world, but just our 2 dimensions gives us a pretty good way to work with things like airplanes and how fast they're moving and things like that, which we'll see problems of that type. So, right off the bat, we need to talk about vector diagrams and then get some practice with them. So we have our vector diagrams where we're going to make sure that we're using lines of roughly the right size, or sorry, vectors, which are just arrows, right? The directed line segment, of roughly the right size to start making sense of this. So typically, if I want to know how fast something is going, I'm going to give you its speed relative to what? The ground. That's pretty natural because the ground, from our reference, doesn't move because we're standing on it. So first little comment. Typically, and it's not always the case, but it'll be really clear if it's not, we want v, and I'm going to write it as a vector here, but I won't, like if you don't, that's okay, relative to the ground. Now, we will see this in a problem either today or tomorrow, but lots of problems like this, navigation on a river, like a moving river, the ground we would look at as the shoreline, like off the river. Okay, so typically that's how we want, but we have to consider everything. So this big comment, we're just going to be able to use to start looking at how do we actually go about combining velocities. And I know that I'm kind of going fast through it because I think the real value of today, not that this stuff's not important, but it's going to be the actual just doing it rather than drawing it out 10 times and then doing it. So our goal with relative velocities is how do we actually combine these when we're in multiple dimensions? So as we think about this, I'm going to have us work a problem and try to get some stuff out of it and make you help me build it as we go. So with that in mind, I'm going to pass you guys out some worksheets. For anybody watching the video not in class with us today, it is 6.3, which I gave you, or is on the Google Classroom. Your worksheet, but just not yellow in this case. Okay, this problem, meant to reprint everything because clearly I tried to make it fit my personal life, but read through the problem and tell me if it makes any sense. Can you guys tell my brain just quit working halfway through? Yeah, so it's like those dumb math memes that you might see where it's like somebody walks in with $10 and they buy this many, how many cucumbers are left at the store? Like, this just doesn't link, right? So we're going to fix this first and foremost.
You didn't do that intentionally?
No, this was completely on accident. Like, I even did the problem in my notes and then I was working it on here so I'd have a key for you guys. And then I looked at it again and went, what the hell? So I think this will suffice if we change the word ball to what? I hate this program apparently. Okay, and change ball to tray. Oh my gosh, this is awful. We're not using that. If we change ball to tray, and I'll have you go ahead and do it, does it make sense now? At least kind of. Because I'd rather not have to rewrite the entire problem, but I'm not saying no to it.
A moving sidewalk like at the airport?
Yep, that's what I'm thinking of. So Zeke, or like in a lunchroom, if we're thinking about a tray, because it'd be weird to just see one floating down. But like, you ever been to our school doesn't have it. Yeah, like TSA. But yeah, that's a much better way to think about it. Okay. If we change ball to tray, doesn't make sense. So the moving sidewalk is just that path that it's following. So Zeke, don't really care who it is, but he's the man. He puts his tray onto this moving sidewalk that's moving west, and then there's a what on the tray? There's an ant on the tray, and this is the only problem it happens with. I don't know how, odd. But there's an ant on the tray, and the ant's walking north. So it's like if we, I'm just going to skip it for a second. Here's a moving sidewalk, and this is an ant. This is what's happening. So just to be clear, here's a sidewalk moving, and the ant is walking on that moving sidewalk.
But he's not walking backwards.
Nope, he's walking perpendicular to the path. I mean, he might be, but I don't think he was an ant. Maybe an uncle. I don't know much about the Jackson family. All right. So, I'm not proud, just so you know. I am not proud of that one. Cool. All right, so Zeke puts his ball. Okay, so his tray. There we go. That made sense. Okay. Kind of. Yeah, that's my bad. I'm glad that I encountered that issue before we talked about it here, because I felt like I was having a stroke while I was trying to figure out what was going on with this. All right. I want to draw a picture first, and we haven't done any of this. When we're drawing our diagrams, what's going to be weird is it's almost like we have two different axes systems, but we're not going to draw both of them. And this is a pretty simple one to start with. We'll get more complex and see what I mean by that. But we're going to use matrix stuff in the easiest sense here. Instead of, or not matrix, I'm sorry, vector stuff in the easiest sense here. And I'm just going to be consistent with it. I know before the break I showed you guys, like, oh, here's 3 ways to deal with vectors. And in hindsight, love that you get the opportunity to use 3 ways. Hate the idea that I've now confused you 3 different times because you're mixing these ideas in your head. We're going to stick with one moving forward with this stuff. And we'll see it again in pre-calc, but we're not at it in pre-calc yet. Okay, let's check it out. I want to at least draw this picture, and it's just going to be a couple vectors put together. What should we focus on first? 2 things are moving, right? There's a tray moving, and there's an ant moving. Doesn't matter which one we deal with first. Do you have a preference? Okay, so if I'm going to draw this tray moving, here it is. West is typically left, up, right, or down? Left. Everybody okay if we say, check it out, here's my tray? No, this isn't really my tray, but this is just the motion my tray makes, right? So it starts there and it moves left. Okay, here's the important part. Do you know its velocity? Okay, it's 0.15 meters per second, so super duper slow. With that in mind, I'm never going to write the numbers here. That might not be true. I'm usually not going to, but I do need to make sure we can identify what this is. If I talk about this vector and it's a velocity vector, this is the velocity of, what did you tell me? The tray, and its velocity relative to what? The ground. Okay, my tray is moving at 0.150 meters per second relative to the ground. Somebody that's just watching it without being moving. Everybody cool with that? Okay, on the tray, there's something else that's moving, and I'm just going to tack it on right here. Tip to tail, just like always. What else is moving on this tray? The ant. Okay, so here's the ant moving, and it's moving slower, so I'm going to draw it as a smaller vector. And this is the velocity of the ant. I'm going to use A relative to what? The velocity of the ant, A, relative to the tray. Nice work, Huggins.
Sorry, I kind of stole that from everyone by going up.
You're good. That's didn't offend me. Anybody else like wildly offended? Everybody's super angry, Huggins. I'm sorry. Okay. In the end, I'm asking about the velocity of the ant relative to the ground. Now, I'm not going to promise that the mathematics works perfectly like this, but in my mind, it feels intuitive if I do one little thing. I'm not truly multiplying. That's not what we're doing with these. But if we think to the matrix stuff that we've already seen, AT times TG, what's going to happen when we combine these and we see stuff falls out? It doesn't really fall out, but I'm okay with thinking like it does. I'm left with the velocity of the ant relative to the what? The ground, which is what we're after in the end. Okay, so looking at this, we're going to kick forward with it, and we get a few pieces of known information. And as always, I'm kind of crazy about you writing the known stuff. Totally could probably attest to that. However, I'm going to be ultra crazy with this because we're going to be really clear with everything that we're doing. So I do know some stuff. I know the velocity of what? How am I going to write down any of my knowns? And I'll keep my colors consistent. I'll try to. So I can't just say VT.
Oh, VT, G.
Okay? And I'm given 2 velocities, right? So since I'm already in green, I'm going to say, hey, we know the velocity of the ant relative to the tray. And what is the ant relative to the tray? 0.05 meters per second. And 0.050, but I'm not crazy about significant figures. Okay, here's the other piece. And this is the consistency part that is going to show back up in pre-calc once we get to vectors. Is it going at an angle? Love that I see no and I see maybe. I don't care which side you're on. Check with your neighbor, just gut feeling. Is the ant traveling at an angle? And argue. Pick somebody say yes, somebody say no. Decide who's right. Don't care who's who. Perfect. If you want to draw a compass rose, you can. But what I'm thinking about is if here's my motion happening, oops. If here's my motion on like my diagram, right? There's one axis and here's one axis. I can see that, hey, it is traveling due north. And when we measure angles, always in standard position, which is what we're going to commit to in here, where do we start the angle? Like the initial side, every angle has two sides, right? If I'm from your perspective, and I got to look, that's positive for you. If I said make a 30-degree angle, is somebody wrong if they do it up here? No, but it's weird to do it there. It's much more natural to be here because you want your initial side to be the positive x-axis. Okay, so this is going to get more important when we get wonkier angles, but I'm going to say, hey, the velocity of the ant relative to the tray, sorry, I just said two different things and wrote something different. The angle theta of the ant relative to the tray is 90 degrees. Okay, because on the tray it's walking due north, and even if this tray were traveling in a different direction, we would still adjust, and we will see that happen. Okay, I'm gonna switch to orange, and I think it was this one. What's the velocity of the tray relative to the ground? So 0.150 meters per second. I want you guys, and pause the video if you need to, I want you to find me the angle theta of the tray relative to the ground. And I'll give you a moment. I probably should have had that out loud. If we start at 0 degrees, which is the positive x-axis, west is 180 degrees. Now, there are other ways to set this up, but because I'm not going to confuse you with 4 different ways, this is the way that we're going to do it. Cool. All right. What am I actually trying to find? So I'm looking for the velocity of the ant relative to the ground. How do I write it? A slash or G. Only thing that I didn't like, Sean, is you said V of. Remember, it's the word sub. V sub AG. Cool. All right. Now, is velocity a vector? Does velocity have a size or a speed and a direction? So if I want the actual velocity, if I don't just ask what's its speed, we also need theta, the angle of the ant relative to the ground, because you need both of those things to be able to talk about velocity. Cool. Everybody on board with this right now? Nothing too crazy yet? Okay. Now, going through this, I'm trying to decide where exactly I want you to put this stuff at. We're going to pause here for just a second. We have the problem set up. We're going to kick over to our notes momentarily. Okay, so we're going to resume this in just a second, but we're going to go back to our notes, and I'm just going to put a dash here to say, look, nope, I'm actually just going to move the screen. Why would I do a dash? I have infinite canvas. Weird. I actually don't have infinite canvas either, so I don't know what I'm talking about at all. Okay. As we look at this, just so we can try to make sense of this, going through, we're going to give ourselves, do you want to try to derive it and work it out and see it? Or do you just want something accepted as truth along the way? I'm really proof-centric and idea-centric. Okay, so as we look at this, we're going to start simple. So I know we've done this before, but we're just going to do a little bit of trig review in our notes. So this is kind of its own standalone thing. And specifically vectors and trig review. Okay. Looking at, I don't know, any angle. And I'm just going to draw a nice coordinate system here. And let's say we have a vector. and its magnitude is just v. And we'll draw it like this. So we'll say, hey, look, it has some size. Might be 10, might be 20, don't care. Now, that is traveling at an angle, yeah? And that angle would be drawn right here. So this would be our theta in this situation. Everybody cool with that? Okay. Moving forward from here, just help remind me, this diagonal line that's formed by this angle theta and that magnitude, which gets really fancy language, does it have components or parts that you could put together to make a diagonal line? What are those parts? Like there's an x part, right? So I'll go ahead and I'll just draw the x part first. There's this x part or component of my velocity that says, hey, to the right in this picture, I'm going that far. And this is vx. Hate how bold it is, but that's okay. Okay, in the x direction, how do you find this? If I want to know how far over I've gone. Something about cosine. So just cosine theta would only guarantee me that point or that distance if I were on the unit circle of radius 1. Is it possible we don't have a velocity that's exactly equal to 1? So it turns out fairly easy to remedy this. And I think we've seen this before, which is why I'm just going so fast. It's whatever our velocity is times the cosine of theta. Okay, that's what this is. Now, beyond that, we have a x component that's just the magnitude times cos theta. But we also get this lovely vertical component that says, hey, look, I'm also going up. Diagonal is just up and over, or down and over, depending on the point of view. I would call this the component y, so vy, and only one minor change needs to happen. It's however big that velocity is, but cosine doesn't represent the y values. Sine does. Remember, x, y is alphabetical, so is cosine sine. This is v, the magnitude, times the sine of theta. All right, we've talked about that at length before. Everybody cool with that moving forward? Do you want to do a quick check just with numbers so you can verify that we can do it? Whether you write it or not, it's up to you. I'm just going to put on a couple things here. I'm going to say the magnitude of a velocity, and you can just use your calculators for this. Let's say it's pretty medium, so we'll say it's 5 meters per second. At, and I'm going to throw you guys for a loop here. This is just a quick trig example. 17 degrees west of north. Okay, a little bit of scratch work if you need. I'm just going to show my solution and talk about it, but I'm going to give you guys a minute to verify for me. I want you to find me the components of my velocity in the x direction and the y direction. If this is starting at north and 17 degrees west from our initial point, you're going to be tempted, and it's completely reasonable that you could call that theta, right? That'd be your 17 degrees. However, where do we start when we're measuring angles? Louder, but I think you said the right thing. As long as you add positive in there, I'm good with it. When we use theta in here, this is the angle that we're going to use from the positive x-axis. This is going to make it so we all do the same thing and we don't get wonky with it. What is this theta? 90 degrees first, right, from west to north, and then another 17 degrees says this is 107 degrees. Okay, once we have that angle discovered, is the rest of this hard or is it just plug and chug? It's just plug and chug. So, if we want the velocity in the x direction, vx, all we have to do is just run through. What's the magnitude of my velocity that I could also just call the speed? 5, and which one's x, cosine or sine? Cosine, so it's 5 times the cosine of, what's the angle we decided we're going to use? Try 17 for me. Like, if you have a calculator, type it in, because we're going to see something wonky happen with it. I'm going to use 107, though. So, and this is the weird part, and without going into it, 17 would work. You could use it, and you could make sense of it. We're not going to. What is this? It should be way less than 5. Probably kind of negative. Negative what? 1.1462? Or 1.462? I just don't have a calculator is the only reason. 1.6. Okay. Negative 1.6 is the number I'm waiting to get a second for. 1.46. You got 4.9 when you did
5 coast 107, but for 5 coast
17.
17, it's negative 1 point.
Negative.
Okay, can I borrow this for 2 seconds? Okay, I'm going to make you guys do a couple things. There's a... Totally lost my train of thought here. There's a mode button next to second. Click it. I'm not trying to flip you the bird. Okay, right off the bat, third from the top, you see a box that says radian and you see a box that says degree. Which one is highlighted for you? Okay, so we got both of them. If radian is highlighted, couple questions. Can you tell me what a radian is? So you can tell me things related to it. I'm good with that for now. Is a radian a degree? What mode should your calculators be in here? Degree. If we change this to degree, I'm just going to go down, highlight, click enter, and as long as I see it's highlighted, I can quit out. And I try this again. I get 4.78. Okay. Now, that's 17. Just kidding, we type in 107. I had a typo. And it's probably the same number. Negative 1.46. Okay, that's in the x direction. Now that we're all in degrees, do me a favor, find me y as well. That's 5 times the sine of 107.
Will we need to put the load back and freak us?
Not today.
No.
Eventually, I'll have to move back and forth.
What does the radian do?
Makes math make more sense.
And like what kind of answers will it give you?
Typically with pi and stuff in it. But you'll get all the same answers, you just have to adjust it. 4.7?
It's for circles.
Okay, now, since these are velocities, meters per second, that's just a quick review of the trig stuff. Now, we have like 3 minutes. We're going to start that problem right away at the start of class tomorrow. I'm going to do one more little example of just looking at how these things are going to look when we actually draw them. Okay, hypothetically, and you don't have to draw this out, let's just talk about this with the remaining time. If I had a vector that went at this angle theta, and we'll go, let's say it was started here and went up there. There's a theta. Okay, and then on top of this, I had another vector that maybe I change direction, I do something like this. If I want to, I think it's natural to think of there being an axis here and an axis here. I can get theta, and I'll go blue. I can tell you what angle that first one's traveling at relative to the horizontal, because that's what we're always going to do. Everybody okay with that's a theta? Now, just to make it up just while we're talking, maybe that's like, what, 130 degrees-ish? Okay, hypothetically, let's say this angle right here is like 70 degrees. If I wanted to find the angle that they're traveling at just by adding them, you think we could? Like, if we go here, we're going to be able to work this out. How would you do it? Not asking for necessarily the right, but if I want to know what angle is just here, how would you indicate that? Say that again. 130 minus 70? Anybody else? Maybe? I might have misspoke. Minus 90. That seems reasonable to me. Do you guys agree with that? Okay. Now, if you're okay with thinking about vectors in this sense, tomorrow's stuff, once we jump into the lesson, we're just going to use this exact same idea. But if I wanted to know just the x direction here, I could do the Vx, whatever this is, cos of 70 for this one, and cos of 130 for this one, right? And I just see they're working at different angles from the horizontal. If that idea clicks, this stuff is going to be so much easier than it has been historically when I've tried to do this different ways. Cool. Everything from the horizontal. Awesome. All right. CAL. Nope, just kidding. We've got a minute. Never mind. You guys can grab your phones for now if you want. Don't text people. There is, unfortunately, no homework this evening. I'm so sorry.